Okay, everyone, can you hear me and see me well?
Yes, we can.
Okay, Megan, can you tell me if I should wait or proceed for more folks to join?
It's 32, so I would go ahead and proceed.
Okay, thank you. I'll do that. Okay, hello everyone. My name is Shivendra Agrawal, and I'm a final year PhD student here at CU in the Collaborative AI and Robotics Lab, or the Cairo Lab. Uh, Broadly, I work towards building assistive robotics for empowering humans with visual impairments to independently perform day-to-day tasks. So today, I'm going to talk about two of my previous work and my current work. So I think the way the session will work is you'll have time to ask questions at the end. I'll try to keep it very short, but feel free to ask clarifying questions in the middle. So in that case, either write on the chat or just pause me. Okay. Uh, so my first work concerns social navigation guidance. And the first paper in the series, it's called a novel perceptive robotic cane with haptic navigation for enabling vision-independent participation in the social dynamics of seat choice. Okay, so I will start by reminding all that being able to interpret and act on social norms is a critical part of our everyday experience with the world. One important example of this that sighted people often take for granted is the ability to find a place to sit. So imagine how difficult this task might be if you didn't have the ability to see. Okay, so in this table from Wang et al.'s ICRA 2017 work on navigation assistance for visually impaired, we can see a list of common mobility tasks uh, and how blind people rated them both in terms of importance and how well a white cane addresses these tasks. As you can see, finding empty chairs in crowded public spaces was the highest rated task in terms of importance, as well as the lowest in terms of the existing solution utility. And it turns out this is a fairly difficult and nuanced problem to solve. Okay, it is not enough to just identify a seat's location. We also have to be able to identify whether it's appropriate or not for us to sit there. So a prior work by Stat and Groot showed that people prefer to seat themselves in a way that optimizes for privacy and intimacy. For example, I think most of you can recognize this area. This is the photo taken at the engineering lobby, the south lobby. You can see that people like to take seats which are closer to walls, which we'll refer to as anchored seats. These seats are more private than the unanchored seat in the middle of nowhere. We can also see that these students optimized for reduced intimacy as they chose seats away from strangers. This mental optimization process also helps them avoid seats that may be taken. So common navigation aids like white canes and guide dogs have some limitations. For example, canes cannot find empty seats in any targeted capacity. And while guide dogs can be trained to locate empty seats in some cases, they are extremely cost prohibitive. And they don't scale well to the population of approximately 43 million people living with total blindness or 295 million living with moderate to severe visual impairment. There are cell phone apps like Be My Eyes, but they rely on the availability of a human for the guide function. So let us jump straight into our solution that we proposed. So our hardware system is primarily composed of RealSense cameras and vibrational motors mounted on the cane with a backpack-worn laptop to run the computer vision and navigation algorithms. So our software system starts with perception. We map the environment, we localize ourselves within that map and identify people and things in the environment using onboard SLAM algorithms and object detection algorithms. We then use a Kalman filter to track detections and handle data association. Once all the things are located in the environment, we score the goals. We score the goals, and then even when a goal is like selected, we path plan towards that goal. Finally, we we use auditory feedback to provide a plan overview, and we use vibrotactile feedback to provide online navigational guidance. So let me show a demo of how the system works before we delve into the methods. So in this room, we can see a scenario with two chairs in the room, along with a bunch of obstacles. These users are novices who have never used a cane. But as you can see, this novice user is not able to locate a chair without guidance. But with our system, the user is able to find the more private chair close to the walls, rather than the one in the middle of the room. In another run, the system notices another human, and this time it leads the user to the chair with lower intimacy. Okay, so that was an overview of what the system does. And let me now talk about how we score the goals. In this case, the seats and chairs were our goals. So once we have located the chairs, we consider a fixed number of rays coming out radially from each chair. Okay. And our key insight here is to overcount contiguous obstacles, which are similar enough to walls and can be used to quantify a notion of privacy. So for example, we use a sliding window whose job is to overcount contiguous obstacle, and it doesn't overcount smaller objects. And that is why a chair's anchor score is raised when it's closer to contiguous objects such as walls. We also formulated a sub-score called proximity score. And the proximity score is affected by the chair's relative position with respect to other socially meaningful objects, humans, and the user itself. So for example, we increase the proximity score if the goal is closer to the user. In this case, you can imagine the seat to be the goal. We also increase the score if it's closer to objects of similar class. Because, for example, a cluster of chairs may increase the chances of successfully finding a seat. We decrease the score if there are nearby objects that are associated with a higher chance of seats being occupied. For example, a backpack or a mug near a chair. We also decrease the score if there are other humans close to the goal to lower the intimacy with strangers. Finally, the plan is conveyed using two modalities. We generate a semantic description of the goal's relative location with the following template. It's a goal object found about dash meters away in the dash o'clock direction. And in the vibrotactile modality, bearing error is encoded into two distinct haptic animation patterns on each motors, creating these 5 possible codes for conveyance. Okay. We also conducted a pilot study to test the components of our system, where we worked with 6 blindfolded users that navigated through 6 scenarios using 3 different room layouts to find a chair. Room 1 is a baseline single chair scenario. Room 2 and 3 were designed to test the goal scoring capabilities. We witnessed a 100% success rate at finding any seat. And we got 83.3 percent success rate at finding the socially preferred seat. And even though the rooms had obstacles and walls, the users often were able to completely avoid collisions using our system. Participants also reported a positive user experience in terms of confidence. Okay, so now moving on to the second work in the series, and that concerns like fine-grained grasp guidance. Okay. And the paper that I'm going to talk about is called Shelf Help empowering humans to perform vision-independent manipulation tasks with a socially assistive robotic cane. Okay, let me again remind you of the challenges of this task. Grocery shopping is hard for people with visual impairments. They usually work with sighted guides that causes a lack of independence. The lack of independence also has other negative connotations, such as a loss of privacy. And finding a product is a very hard visual problem in itself. In the US market alone, they introduce around 30,000 new products each year, presenting a huge challenge for modern day computer vision algorithms. Moreover, grocery items are often very similar and densely packed, making it hard to differentiate them based on tactile feedback. So we repurposed the navigational cane that I just talked about. It still has real sense cameras mounted on the cane with a backpack-worn laptop. And the perception and planning algorithms are done on the laptop. And sensing with the cameras is still mounted on the cane. And guidance is provided verbally via the laptop speaker in this case. Okay, before we proceed, I'll briefly mention our core contributions of this work. The first one is that we presented a modular two-stage computer vision pipeline to locate desired products in a grocery setting, and then followed by a novel fine-grained manipulation or grasp guidance system that optimizes for guide time and number of commands. Okay. Again, before I talk about how the system works, let's see a demo of the system in action.
I found the product at about 11 o'clock direction. Move 6 inches up. Move about a foot to the left. Move far forward. Move to the left. Move forward. Go ahead and grab the item.
Okay, I think the audio was very faint for you, but there were commentary on the slides. So essentially, for this problem, we assume that we are in front of the correct shelf. But even then, the problem of locating the desired product and grasping it is challenging. And this particular project aspects that particular portion of the whole task. So the workflow follows a serial architecture in this case. And as the first step, the system issues commands to assist users to align the cameras with respect to the plane of the shelf, such that the camera is facing upright and straight. This is followed by detecting the products and performing data association. Once the target is selected, the system creates a guidance plan using a Markov decision process-based formulation. And finally, the system provides verbal guidance, which starts again with a plan overview where the user is informed of the general direction of the product and is followed by movement instructions such as move 6 inches to the left. Okay, we'll now see a walkthrough of how the algorithm for product detection works. To use the system, we require that the user has access to a single image of the product that they want to find. The product detection algorithm has two major stages. In stage one, it proposes regions most likely to contain any products, and we train a YOLO v5 to achieve this. So given a scene, in stage one, the system proposes bounding boxes that are likely to contain any product. We don't know yet which product, but just any product. In stage two, we trained an autoencoder and use its learned encoder as a feature extractor. We use this to extract visual features of the desired target products. And we follow this by extracting the features of each of the proposed regions. Once we have the features of the target product that we already had to begin with, and all the proposed regions, we compare the features to find the best match. And features are matched using cosine similarity in this case. The best matched region is then selected as the target product on the scene. Similar product instances from each frames are also associated with past observations to build a persistent product mapping. And we use depth and IMU data to locate the product with respect to a fixed global frame of reference. And once the target is located, we use a Markov decision process or an MDP-based planner to compute a guidance plan. The MDP is formulated from human hand movement data collected through a prior experiment with blindfolded participant. We basically recorded a mapping of verbal instructions to human hand movement. You can see a sample of verbal instructions in orange here. And the plot of movements it caused next to it. We then fit a Gaussian on this hand movement data that gives us a mean and a standard deviation for each verbal command. Finally, we formulate the guidance planning problem as an MDP, where the set of verbal instructions make the action space. The mean and the standard deviation from the Gaussians help us form the transition probabilities. And the discrete remaining distance to the goal forms the state space. We designed the reward function to encourage reaching the target efficiently and discourage issuing superfluous commands. So it also discourages our system. The reward functions also discourages a sequence of commands that could be illegible or frustrating by penalizing axis changes. For example, you can imagine that it could get quite annoying if the system asks you to move, like right, then up, then right, then up in an interleaved way. So finally, we solve the MDP offline, but we query the generated policy online to obtain the best action, which in this case is the best verbal instruction for any given state. Okay, so to evaluate our system, we conducted an IRB-approved study with 15 novice blindfold users for system testing and validation. And this was a within subjects study with each user retrieving 5 different products in each mode. So we did a 3-way comparison between shelf help, that is our system, the baseline, and a human. So shelf help is based on the MDP formulation, and it issues instructions like this, like following. So move 6 inches to the left. And the baseline continuous planner is based on visual servoing, and it issues instructions like keep on going left. And then it asks you to stop. And we evaluated and compared the 2 planners with each other and with a human guiding over video call, which we consider to be the gold standard of assistance. The human caller in this case gave free-form verbal guidance. Okay, let us see some of the results. On the left, you see the average number of commands issued by the planners, and on the right, you see the average guide time spent by the planners. Through Tukey's HSD statistical test, we confirmed that shelf help outperformed the baseline continuous planner in terms of number of commands and guide time. And we also observed that shelf help matched human level assistance, which we confirmed using a 2 one-sided t-test, which is a test of equivalence. Yeah, so like merely saying that 2 things are different is not enough in this case to show that shelf help actually statistically matches human level performance. We need to do additional tests. Okay, so to conclude this work, we saw that independent grocery shopping is a challenging visual task for the blind and visually impaired people. Our system, Shelf Help, takes a first step towards breaking barriers on this task by providing a technical solution to the product retrieval subtask. Shelf Help can locate items and verbally provide fine-grained grasping guidance, enabling people to independently locate and retrieve items from shelves. The user study revealed that Shelf Help objectively matches human-level assistance, but it falls short on human-like interactive metrics. Okay, now I'll talk about what we are up to right now in the lab. So the next piece of the puzzle of grocery shopping is navigation in the store. And navigation in the store is a really hard problem for autonomous systems because, for example, this problem of figuring out where your precise location in aisles is very challenging and something that is unsolved. And the what makes it hard is the constant change in product poses and stock sizes of the products and place and that makes it very challenging for modern day SLAM algorithms for and because most of them assume the scene to be static, which is not quite the case for shelves and aisles. Okay, so how do we solve this? Before giving an overview of our current solution, explain some basic concepts involved. Okay, so we create a map of the scene. So what you are looking at is a top-down view of a map, so where you basically divide your 2D world into grids and then fill each of the cell with the probability of that being occupied. So in this case, the white color here represents free space, and the gray color here represents unexplored space, and the black borders represent obstacles. Okay, so we create a map, and then localizing on a known map or finding your position on a given map is called localization. And in robotics, people do that using sensors. So for example, so imagine this is a top-down view of a room, and then you don't know where you are at. So in the beginning, your hypothesis would be that you could be anywhere in the room if you don't have any information. So, and these blue dots represent your guesses, which could be anywhere. And then imagine that you take some measurements. You take some measurements and those measurements are shown in red here. That can help, and you can match those measurements with the actual map. And that will eliminate a lot of possibilities, and this can help you figure out where you are at just by a single measurement here. So this is broadly the intuition towards what we are working with, and so an algorithm like this exists. Okay, so what we did is we added a semantic layer on top of that. So what our system does is it looks at all the products and it classifies them and it converts them to a discrete distribution. So this is actual footage from the lab. Okay, and that helps us to create a semantic mapping of the shelf. So this is a 2D top-down view of our mock grocery store that we have in the Cairo lab. And all these different colors represent different classes. So now we have a semantic map, which has more information than just the occupancy information. We do something called raycasting on the semantic map. So basically, it tells us so for each possible position that is possible on the map, we try to figure out what you would see if you're standing on that position. So for example, you see, like if you're facing the shelves, you'll be able to see some semantic information, and the semantic information is shown on in green here. Okay, so that helps us to create a system where given a scene, we are able to classify that scene into a discrete distribution like this. And then because of raycasting, we can guess locations that are most likely to contain that are most likely to be correct. Okay, so there are only so many places in the map where you are expected to see this particular distribution of products. So our system then take guesses and figures out some locations where you're most likely to see that particular distribution. A small demo of that is that, you see, in here, the system initially started at a wrong position just because it starts randomly. And then when it sees a distribution of product, then it snaps to the correct location. See, here it starts incorrectly, randomly, and then snaps back to the correct location once it observes a distribution of products. Okay, so this is one of our current work. Another current work is about plan conveyance. So say you find things on the store, but there's still is a difficult task of guiding a human to that location. And we realized that we don't know the best way to communicate high fidelity navigation instructions when the user's hands are not free. And there are many common scenarios for that. So when you're holding onto a grocery cart, when you're holding onto uh, the baby cart, uh, I think the word is not cart for that. Anyways, so we are currently experimenting with some vibrotactile device prototypes, and we are also optimizing for their placement uh, and so we will evaluate this through a thorough user study. Some other open problems in this particular domain is that we are trying to address is need finding. Where we want to conduct structured interviews with people who are blind to prioritize the problems, to understand the needs, and so that we don't solve for problems that are not required to be solved. Uh, there are some computer vision problems in this domain that are unsolved. Like for example, locating discount prices and sale prices. And then one of the major problem is to search a product on the map so that you can take the user to a product. These are some open problems that we are currently working on in the lab. And yeah, apart from that, I think I'm done with my talk and I'm open for questions, and I'll leave the screen where you can see my contact if you want to contact me. Um, Megan, should we stop the recording, or should the Q&A be part of the recording?
Yeah, I can go ahead and stop it so people feel comfortable asking questions.